All right, everybody. Hello and welcome to the show. My name is Nick Larson. Today is November 7th, 2019. It's about 12:12. I'm a little bit late, just like always. What we're going to work on today is... Let's pull it up. The incognito window. We were working on some stuff very recently where we said we wanted to go to... What did we say we wanted to go to? Monte Carlo tree search. That's what it is. Okay, Monte Carlo tree search. The part that we have implemented is pure Monte Carlo game tree search. And what we want to do is look at exploration and exploitation. So let's take a look at the problem that we have. Let me close this. File. Close workspace. Close folder. Okay. If we go to Monte Carlo tree search, what we have... Load up all your stuff. Load up all your stuff. When you're done, let me know so I can do my... There you go. Okay. Okay, so we have a game, and the game plays, and it plays... it plays player 1 versus a Monte Carlo tree search player, which is great. Oh, goodness me. Now, just to show you, let's go ahead and actually play a few rounds here. I want to go to ICD, Culture of Development, LS, CD space, Monte Carlo. Oh. Where did I... Oh, Monte Carlo, that's what it's called. CD Monte Carlo tree search, LS, CD space, SRC, LS, CD space, MCTS, LS. And then in here, we want to say CD bin, LS, LS, CD debug, LS, CD space netcore app 3.0, LS. And here we want to say mcts.exe. Okay, this is going to let us play it so that you can sort of see how it works here. Can I zoom in? Because that would be awesome. I can zoom in. Okay, and you can see that basically the way that it works is it shows you the current state at the top, which is an empty board currently, and then it says show me all of the successor states that could possibly happen, and then choose the number to choose which one you want to do. And if I do an example where we go with 0, I think we just do 0, 0, 0. What we see is that it prints out how well it thinks it's going to do for each given move that it makes. Now, we happen to know that the game is going to be a tie no matter what. This is going to take a second. So we want to put it, I don't know, probably... Where do we want to put it? Probably in the middle. I guess. How about just do 0? It blocked me. Hooray for it. Oh, and it's 1. Great. Okay, so it found that it won. Let's do it again. The problem that we're going to get to... Oh, man. I never do this. I'll go. Happy Thursday. Thursday. Monte Carlo tree search. Exploration and exploitation. There we go. Let me refresh this. Does it not change when you're live anymore? And it should be 86. Save again. There we go. All right, perfect. Okay. So, oh, this is getting slow. Why is this super, super slow? I mean, like ridiculously slow. Okay, what do we want to do? We want to play at the top again. Oh, this is busted. There we go. Okay. So it decided to play in the same place again. So now I'm just going to play in the middle, which was 3. Okay. And it decided to play down in the bottom left-hand corner because it thinks it's a tie. So in this case, it worked out again. Let's just go ahead and let it win. Okay. Again, 0. Alright, this time it played in a different place. And this time is actually bad for it. Okay, let's take a look at why this is bad. Because this is a guaranteed losing position for the O player. In this case, what we're going to do is play in the bottom right-hand corner, which forces it to play in the center, which then forces us to play in the top right-hand corner, and then gives us a win right here and a win right here. So it has chosen a move that is guaranteed to lose at this point. And that's bad. And we want to fix that by basically adding in... so what happens is it tries all of these moves, and the first one that it tries, it just happens to lose on. And it tries this one, and it just happens to win. And once this one has won, it always has a better score than these other ones right here. And that's bad, because that's just random bad luck, right? We tried this one, and oh crap, it turned out bad. We tried this one, and oh crap, it turned out bad, right? And then we tried this one, even though it was guaranteed to lose, because it was playing randomly for both players, it just sort of, okay, randomly won this first time. And so it decided, okay, I'm going to keep playing this one because it's the only one that looks like it can win. And what we want to do is we want to address that issue by basically saying, look, we have a lot of information here, 993 trials, and it has not won very many of those. So what if at some point we're like, hey, hold on, this is really bad, but these other ones we just don't have a lot of information about. Right? We only have one little piece of information about each of these. So what if instead for those we were like, let's go back and try those again. And that's what the goal is here on this, which is called upper confidence bound. Let's zoom in so everybody can see. Right? And that is what we want to try and implement today. And it's really simple. When you're scoring each of the moves, like as you're going through and saying, let's take a look at it, we're just going to discount based on the amount of information that we actually have. We want this one, Monte Carlo tree search. Okay. So in the place where we do the expansion, so we have a tree search, and what we do is we say perform pure selection Monte Carlo. This pure selection is the part where we want to weight it. And right now you see that we have pure Monte Carlo score. Instead of this pure Monte Carlo score, we instead want to implement a different score. Public double upper confidence bound score. And basically all we want to do now is implement this, and we should not see this problem anymore after this. Alright, the main difficulty in selecting child nodes is maintaining some balance between the exploitation of deep variance after moves with high average win rate and the exploration of moves with very few simulations. The first formula for balancing exploitation and exploration in games is called UCT, Upper Confidence Bound 1, applied to trees. And it was introduced by these folks. UCT based on UCB formula derived by these folks, and the provably convergent adaptive multi-stage sampling algorithm first applied to multi-stage decision-making problems, specifically Markov decision processes, by these folks. Alright, recommend to choose in each node of the game tree the move for which this has the highest value, where WI stands for the wins for the node considered after the ith move. NI stands for the number of simulations for the node considered after the ith move. NI stands for the total number of simulations after the ith move ran by the parent node and one considered parent node of the one considered. And C is the exploration parameter, theoretically equal to square root of 2, in practice usually chosen empirically. Okay. Fun. Very, very, very fun. Most contemporary implementations of Monte Carlo tree search are based on some variant of UCT that traces its roots back to adaptive multi-stage sampling, simulation. Okay, so after the ith move, so basically we're going to take the number of wins. Basically we're going to take this and this needs to be double parent simulations, and this is pure Monte Carlo score times we want a math dot square root of 2 as a constant. Okay. Static read-only double C equals math dot square root of 2 times C times math dot square root of math dot log. I don't know if it's log 10 or log 2. Let's go take a look. Also, this is becoming kind of cumbersome. Let's put it down on the next line. There we go. Natural log of n, where n is the total number of simulations by the parent node of the one considered. Okay, so natural log is just log. No, it's not. Okay, let's look that up just to make sure. I believe we say math dot epsilon e. Yeah, there we go. Math.log. Oh, the natural log. Okay, so it does the natural log if you just do it like this. And we say parent simulations divided by simulations count. That's what that looks like to me. Let's take a look. Can I zoom this? Oh, come on. Oh, I'm muted. How? Am I? I see the voice thing. No, it was you. Okay, great. Also, welcome, man. Good to see you. Okay. So we have the pure Monte Carlo score, which is the wins. It's good. It's really good. Stressful. Super, super ridiculously stressed, but good. I took on a project for Content Lab, the company that like sponsored the jerseys for the stream team. And it is a non-trivial project. And they're like, hey, you have 2 weeks to get this done. And so I was like, had no idea where to start. So I just started like implementing a solution to this thing. And like about 3 days in, I was like, I gotta like actually do some research here. And when I got into the research, I was like, oh, this is just a really hard problem. Like, this is just an exceptionally hard problem. And so I kept grinding away on it and grinding away on it. And then finally I started making some progress. And I write them and I was like, this is a lot of work. Like, just an incredible amount. And it's due tomorrow. And the thing is training now, and we'll see if it works. And I have to write like a 1,200 word like report about it tonight, which I don't think is actually going to be that hard because there were so many problems that I ran into. I'm just going to be like, here was a problem, here was a problem, here was a problem. But the actual like usefulness of this thing that I have built is, in my opinion, pretty close to zero, and I'm a little frustrated about that because like I would not have blogged about this if I had tried this on my own and was not contracted to do it. So there's that stress. But yeah, other than that, work's going pretty good. And now we're going to see if we can make this tic-tac-toe game win or like not lose all the time now. And that's what we're looking at. So we have the pure Monte Carlo score, which is the number of wins divided by the simulation count, which is great. Then we have the C, which in this is square root of 2, which is what we're just going to roll with. And we did that as a constant so that we don't have to recalculate that each time. And then we did square root of the natural log of the parent simulations, right? Parent simulations, total number of simulations by the parent node, and the simulation count. Divided by the simulation count, which is NI again. So this is great. And for this, we also need to... I think we also need to do this. Simulations count equals 0. Then we do 1D, otherwise we do the real thing. And let's go up and figure out where this thing was being used. Pure Monte Carlo score. So not this. Instead, we want to do not pure Monte Carlo score. We want to do upper confidence bound score by successors is state. Oh, we need to look up the state. states of state. And we don't want to do that every time. We want to do parent var parent simulations equals states of state dot simulations count. And then for this, we want to put parent simulations. While not state dot is okay. Okay, and what this should do is basically even out the scores a little bit. The ones that are guaranteed to be losses should just be wiped out. And should not be explored very often at all. And the ones that have a chance of tying or winning should be explored a little bit more evenly. That's the plan. Let's see if it works. We need to go with the old... Nope. Probably, yeah, exit out of this. Okay, let's go here. Let's kill this. Let's do the old... Oh, well... Nope. Terminal. View. Terminal. Okay. CD space src. CD space mcts ls. .NET build. Okay. And then let's try it out. And for this one, we just want to make the good old... Alright. See? Here's what happened. It found some ones that obviously lose. And let's just verify that. And it explored the other ones to some degree. I still don't like how it got a 0 score. I guess these are all... I don't know. Maybe I need to count simulations at the very top. Like maybe that's what's not happening. So it did spread it out a little bit. I still feel like it should have done a little bit better job of spreading it out. There's no reason that any one of these should have been O of 1. Like what value does that actually have? That's what I really want to know. I don't want to just know that. Okay, let's go to where I'm printing it out. This is going to be in the Monte Carlo Tree Search player. Or it's not. It's going to be in the place where I actually print out the moves. States, wins, and stats dot upper confidence bound score okay, let's do that. Current states is a game. Okay, so what we want is expand successors. Okay, so this is where it does the simulation. And then this is me just printing it out. Okay. Oh no, this is me printing it out. Alright, so what I want to do then is say double best score. No, parent simulations equals what should it equal here? Should equal tree.states of current dot simulation count, and then here we want stats dot upper confidence bound score of current simulations. And this should print out, let's build it. This should now print out what the, oh, no. Oh, I'm still running the game. There we go. Now it's built. Okay, and this one, 0. This right here tells me that the parent state is not getting updated all the way back to the beginning with the simulation count. So let's print that out. Let's do console.writeLine current simulations plus current simulations. Let's go kill it. Let's build it. Let's run it. Oh, current simulations is 1000. Somehow, these scores don't seem right. Let's go take a look. Why are they coming out like this? The upper confidence bound. Parent simulations is 1000. Simulations count is 1. So we have a pure Monte. Oh, that is a times. That's probably incorrect. It's a plus. We need a plus there. Okay, that was my mistake. Let's try that one more time. Kill it. Sure. Build it. Run it. 0. Scores. And there we go. All right, that's exactly what we wanted to see. All of the scores of what it chooses should be very close to each other. And then the one that actually gets explored the most in this case is this one. No, it's this one, which it has the most information about in terms of doing well. So it's actually exploring all over the place now, which is great. That's exactly what we wanted. It's finding that these are actually pretty bad. Right? These are only winning like 1/4 of the time in a random drawing. So let's go ahead and play again. It decided this time it was going to play at the very bottom right here, which is an actual tie. And so we want to play somewhere that will actually force a tie, which I think you can do. Well, there's only one win that it can do if you play in one of the corners. So let's do that. Let's play on the bottom left corner. So let's play 5. Okay. And then it correctly recognizes no, it doesn't. Which move did it actually make here? 7058. Playing here. It thought was only a win 16. It thinks it's going to lose. It is gonna lose. No, it's not. Why does it think it's gonna lose? It basically thinks no matter where it plays, it's going to lose. Was that just a bad random selection? I guess then we play what? Oh, it is going to lose. Right, if I play in the top right corner. Wow, that's weird. So if I play in the top right corner, we win. One. And then obviously we can win if we play 0. Weird. Okay, let's play in the top left corner again. This time it played in the middle. Okay. It thinks it's going to tie here. I should really print out the Monte Carlo chance as well, just to make this easier for me. Like the pure Monte Carlo chance is just like the number of times it randomly won. So it played in the middle, which was good for it. And that is a tie. Like pretty much no matter what. So I think we play... What, 4? Sure, let's play 4. Okay. It correctly blocks us, thinking that it's actually going to win. So then we have 2. We need to block it. It now plays at the bottom. And I believe these all are ties. Yeah. Okay. And it explored 317 the most. So it took that one. No, it didn't. It took... Oh, it did 317 twice. Got it. Okay. So then we just play at the top. 0. And then it knows that if it plays down here, it loses. That's what this is. But do notice that it explored it 36 times as opposed to just trying to straight up win. Okay, great. So then we just do a 0 and we go on. All right, the game was a tie. Okay, so it made a bad move. It seems to like making bad moves. That's really interesting. That's really, really interesting. Okay, let's print out the real Monte Carlo score as well. The raw Monte Carlo score. And this is a little difficult to read, so let's put a new line in here, I think. New line. 1, 2, 3, 4, 5. And this is going to be pure Monte Carlo score. Pure Monte Carlo score. Okay. Kill this. Run it. Okay. So it thinks this one has the highest chance of winning, but it explored this one the most. No, I'm sorry, this is a higher chance of winning. God, what am I saying? I can't even read. Okay, so this one it thinks has the highest chance of winning, so it plays up here, which is awful. I've never tried implementing anything like this. It's pretty fascinating. Yeah, I agree. I'm trying to... I sort of thought it would just be smarter than this, you know? I mean, it's still interesting, but it's like, I thought it would just, for a game like Tic-Tac-Toe, get to the point where it doesn't lose pretty quickly. Maybe 1,000 simulations just isn't enough. Maybe if we jack it up to like 10,000, it would be faster. Or maybe if we let it run for a full second and however many it gets done, it gets done. Because I don't mind waiting a second to get a move. Like, it doesn't have to be instantaneous here. So it chooses this move, which is a loss. And we know it's a loss because if we play here, it's forced to play in the middle. I play here, and I have a win here and here. And somehow it did not figure out how to recognize that. So let's go ahead and do that anyway. Which is 6. And it should know pretty well that it has lost at this point. Yeah, it thinks its chance of winning is no more than 18%. And it happened to take that one. But it knows, like, it's a loss at this point. So let's go ahead and lose. This is going to be 3. Now it should really know that it's a loss. Yeah, it thinks there is an almost 0%. It thinks there's a 0% for this one. It thinks there's a 0% for this one. It thinks there's a 0% for this one. And it randomly happened to win a couple of times with random movements on this one. That's interesting. Okay, let's let it wait for a half a second and see how far it can get in a half a second. Your opponent looked away and you wrote it in for them. Yeah, yeah, basically. The 4-year-old thing is real. My kid's 6, he still can't play tic-tac-toe and win. He's just like, yeah, you just put it on there. Okay. Okay. Let's do a time limit. Let's not do a Monte Carlo tree search. Let's do a time limit. Time span. I don't actually want a time span here, do I? Maybe I do? No. Let's just put int milliseconds to move. Okay. Int 1000. Int. Okay. Long iterations equals 0. Okay. Actually, I don't even want it like this. Just want... Okay. Datetime.utc now. Stopwatch. stopwatch equals stop dot start new using system.diagnostics. And then we're just going to say I++, and we're going to say if I mod 1000 equals 0, then we're going to do a time check. We're going to say if stopwatch dot elapsed milliseconds what's the right way to do this? We basically want to figure out what the average time is. Okay. Why not just check the elapsed time past your time limit? Well, if you're past your time limit, then you've, I guess for the point of this, I guess it doesn't really matter. So yeah, is greater than milliseconds to move, then break. So it turns out that like this operation right here is actually really expensive. That's what this is about. This can take upwards of a millisecond in some cases, as crazy as that sounds. It's usually not a millisecond, but there are cases where it cannot be fast. And then this is also doing a bunch of conversions. So when you go through this, it's not just grabbing milliseconds. Like it's going through if you go look at the actual internals for it, it's just not good. It's just really, really, really bad. So we're only going to check it once every 1,000 or so iterations. And this number should be configurable. Like that's why I was trying to like figure out an average, because you wouldn't do this. You would sort of say like, okay, tell me how much I got done in the last 1,000 and then estimate how many more I can do is the way that you would approach it. So stopwatch.elapsed milliseconds greater than this, then bail. Okay. And maybe not. Let's make it a long, just to be safe. Okay. Let's try that. And the milliseconds to move, right now we're putting in 1,000, which is 1 second. We don't want num rollouts. We want time milliseconds to move. Okay. And then there was a second reference here. What was the second reference? Oh, sure. Yeah, whatever. A debugging test? Yeah, whatever. I'll take that. Okay. And then we have... yeah, this is going to be milliseconds to move, actually kind of like 1,000 there. Let's do 500. So that it still seems really fast. Okay, so checking it too often will artificially inflate the runtime. Absolutely. It will decimate the runtime. Like, that's the best way that I can put it. Like, if you put for it to evaluate once every loop, like, you would see a reduction by, I don't know, probably like 100x in the amount of work that it could actually get done. It's really, really bad. Okay. There we go. All right, it waited a half a second. Okay, it thinks this is a tie. So hopefully it went with this one. And look, it did a lot of simulations. It did 16,000 simulations. Which is much more than the which is much more than the, what do you call it? 1,000 simulations, which is much more than the 1,000 we were previously doing. And in this case, it actually found that the center move was the only decent move. Which is good, right? So now let's move somewhere. Let's go with, you know what? Let's go with the bottom one, 6. Okay, it's been a half a second. It thinks there are 2, 3, 4 moves that'll tie, and 2 moves that are a loss, or that have a much lower chance of winning. Is that cumulative simulations? Yes. No, it's not. So the reason it's getting faster is because it takes less time to play out the rest of the game the further into the game that we get. So instead of it having to guess all 9 moves, it only has to guess, 4 moves or whatever. So let's go ahead and choose something where I have an opportunity to lose. All right, we're going to go with 0 on this one. And you'll see on this one, it's probably going to like shoot through the moon. Well, 53,000, that's still quite a bit. And if I had to guess at this point, okay, so it thinks now that all of these are losses unless it actually blocks me, in which case it's a tie. So it has figured out that we're going to lose if we don't block you now. Which should be true. The current state was me blocking them. Oh, wait. Any of the other moves are... Oh, yeah. If it doesn't play here, the other 3 moves are a loss because I just play there. That's right. Okay. So now, yeah, the last chance that we have to win is either this or this. So we play either one of these 2. And in this case, we're just going to go with... we're going to go with 2. And then it knows that this one is a tie and that this one is a loss. And so it chooses the tie. Okay, that's great. All right, so I think the time-based thing here is obviously working better than just saying do 1,000. I want to say that we could make this much faster. And then we would be able to get deeper into the games, and that's probably a better way to go about it here. Let's go ahead and... All right, it was a tie. So on the first one, let's go in the middle. Yeah, on the first one, it's getting through like 16 or 17,000. And in this case, it thinks it's going to lose. So it plays up there. Yeah, no, this is a tie. So let's go with... Let's go with 6. Okay, it blocks... Oh, it doesn't block me. Oh, this one's interesting. So it finds out that playing on the top right or the bottom left are the only ways to tie, and the rest of them are going to lose. Okay, this is cool. I'm actually kind of liking this. I want to implement a more challenging game and see if it still succeeds at that game. That's what I really want to do. I also want to make it faster. Like, there's no reason this needs to be this slow. So maybe let's do that. Let's go to tic-tac-toe. Right, like all of these right here. Okay. Let's apply move. What does apply move do? That's pretty expensive. So if the board were not an array, and does it need to be? How many of these references are outside of it? It looks like only one is. And what we could do is actually pull that from somewhere else. Okay, so having an array as the state is like, how big is player ID? Probably an int? No, it's a byte. Okay, so player ID is a byte, which means we have 9 bytes representing the board, and we could drop that down to 2 bytes. Yes, we can. For tic-tac-toe, I don't think this really matters. But for the sake of like showing the intent, I think I am still going to grind away on this. Yeah, I think I still am going to grind away on this. Okay, so we're going to have private short player 1 pieces, player 2 pieces. Okay. Can I do it in less than this? I have 9 states. Yeah, I think I can. There are 9 spots on the board, not without combining spots. Can I do it? Yeah, not without combining spots. Okay, so if we have player 1 pieces and player 2 pieces, then we're going to have a little to-do here. To-do, basically get rid of this. And then here, maybe we'll go like this. Player 1 pieces equals 0. Player 2 pieces equals 0. Yep. I think maybe we just comment this out all together, because that'll make it super easy to get rid of it. We'll just get a bunch of errors. So we don't actually want this. We want player 1 pieces equals player 1 pieces. Player 2 pieces equals player 2 pieces. Current player's turn. Okay, if board of cell number wait, next state board cell number. Okay, so now we want current pieces. Okay, if current player's turn equals player ID dot player one, then we want to say next state dot player pieces one, and this is going to be or equals of one left cell number. And I need to cast that to a short 1s. No, what's the trick of having a short? What? So basically I'm creating a bitmap for the board for each player's pieces. Maybe it would just be easier if I make them ints. And then none of this would complain, and then we can worry about shrinking it down later. Okay, so now this is not going to complain anymore. Alright, so the idea is, if it was your turn, if it was player one's turn, and that's the person who moved its cell number, then what we want to do is mark cell number as a 1. We're doing a bitwise OR, so we're saying set that bit equal to 1. No matter what's in player one pieces, left shift the 1 that many times. So if they chose to play in cell 0, then we're just going to have a 1, and it'll play it in the very first spot. If they wanted to play in cell 3, it'll shift 3 over and put it in the third spot. So same concept, only now we're going to do this as player 2 pieces. And then we don't need this anymore. And we need determine winner. Okay, great. Determine winner. Okay, that's private, so we can do whatever we want to do here. And what we want to do is pass in. I got an idea from this, might not be relevant. What if you just keep track of the order of plays, then use 1 bit to mark which player started? So what if you just keep track of the order of plays, then use 1 bit to mark which player started? So the way that I'm trying to use this later on, right now actually, and determine winner is, this is slow, right? And this is slow, this like giant for each that then has to look at each of these different cells and determine if they're all the same. So now what I want to do is I want to basically just say whoever just played is the only person who could possibly have won. So give me just their pieces. And then to check whether or not they actually won becomes a bitwise AND. And as long as the bitwise AND matches, then they have won. So that's it. Int pieces That's it, just int pieces. Right? And now what we do is we change this and we say this is no longer going to be an int array. This is going to be an int array. And the way that this is going to work is we're going to say 1 left left 0 or 1 left left 1 or 1 left left 2, comma. Still works with parity checks for odd versus even numbers, and you can also track the full game history, but yeah, trade-off is, I guess, changing the binary board to an integer board. I'm just not sure. Okay, so talk me through this a little bit more. What if you just keep track of the order of plays? How would I do that? There are 9 possible moves on the first move, so I need at least 4 bits to track the location of the move. Or am I misunderstanding? Okay, 3, 6, 0, 1, 2, 0, 2, 4, 4, 5, 4, 3, 7, 4, 5, 8, 6, 7, 8, 8, 6. Okay, so now this gives me all of the winning locations, all of the winning configurations as just integers, and then all of this in here becomes actually and then int player ID last player's turn. Last move player. I was thinking about this from the perspective that there are always 9 spots to choose the first move, then 8, then 7, and those moves always fall on the first, second, the first player. So using numbers and an array of size 9 gets you all the possible combos. Right, it's the array of size 9 that I'm trying to get away from, because copying an array of size 9, even if it's just bytes, is still fairly expensive. It's an allocation, right? I gotta go and like grab some amount of data and allocate it separately from the actual tic-tac-toe class itself. Right now, tic-tac-toe is a class. If I can get to the point where I can switch it from being a class to being a struct, then we're in a very winning spot, because instead of having to allocate this and having to allocate this for each new class that I build, it can instead just allocate this one, which would be much faster. And then also these lookups are going to be a whole lot faster, right? So the idea now is we say if pieces and cell group equals pieces, and why is that complaining? And cannot be applied pieces and, there we go, then return last move player. Okay, so that's what determining the winner becomes. And in fact, it's probably easier to now switch this. No. What all calls this? Only one thing calls this? Probably easier to have this not return this and just return a bool instead. Return true. Otherwise, return false. Now I don't need this. Now I can go look at the place that calls this. It's determine winner. And we're going to have this be in here. Equals determine winner of next state dot player one pieces, then player one dot player one or player ID dot none. And then this as well can go down here, and this is going to be player two. Okay. If next state dot winner is player ID none, and there are any cells that are empty. Okay, so we need any cells that are empty, which is actually pretty simple. We say, okay, int all taken equals next state dot player one pieces or next state dot player two pieces. This will show us all of the ones that are taken, and then we can say all taken and 0x, and the way that we want to do this is it needs to be a 1ff. So what this says, okay, equals, or let's say like const int all slots equals 0x1ff. And we say if all slots, if all taken and all slots. So we have marked the first 9. Oh wait, here we go. This is some nice stuff to think about. Cool. So what we've done is we have marked the lower 9 bits, and F is 4 bits that are all positive, that are all 1. And then a 1 on front of that. So this is 4 bits, 8 bits, 9 bits that we have marked, the rightmost 9 bits that we have marked all as 1. And then we're saying if all of the taken bits and all of the slots is all of the slots, then we have verified that they're all gone. So we know that the game is over. Oh no, not equals. That's what it is, not equals. Do we want 8 bits or 9 bits? The last move is always forced. We want 9 bits because at the end of the game we want to leave the next player as player none, because that's how we signal the end of the game. And in fact, I think this else statement is actually not really useful at all. If the player ID is none and something else, like this never gets hit, so we don't actually need this, because only when the oh wait, hold on, now this is confusing me. Okay, let's see what it was before. I'm just going to copy all this. And then we're going to go backwards to see what it was before. Okay. If the winner is none. Oh, that's what we decided. Okay, if the winner is none. Yeah, we do need this. Never mind. We do need this. Just reading it wrong. Alright. If there is no winner but all the slots are taken, then we set the current player's turn to none, and that signals the end of the game. Okay. We still have some red stuff here. Expand successors. Enumerable.range, which in this case we're just going to put as 9 because we happen to know the answer. Okay? Const int all slots equals 0x1ff 0 to 9. No. This is not what I want. I want all taken. Equals player 1 pieces or player 2 pieces. Then I want to say where all taken right shift M equals 0. Oh, crap, that's not right. And 1. Alright, so this says shift it right this number of times, and the and zeroes out everything except the lowest bit. So if that bit is 0, then I want to create that next move. Okay? And then is terminal winning player number equals winner. Okay, that one actually seems like it's fine. Board.length. Okay, we don't need this anymore. Instead, we need something like player 1. Okay. Int hash code equals int hash code equals player 1 pieces dot get hash code times some very large prime number. Give me a very large prime number. Large prime numbers. Let's go with, I don't want the largest known prime number. That's not helpful. List of primes up to a very large number. Okay, next page. Next page. That's pretty large. Next page, next page, next page, next page, next page, next page, next page. Oh no, not 200. Let's go to 600 per page. Next page. There we go. Next page. Here's a good one. Times this. Or player 2 pieces dot get hash code times or equals times another very large prime number. Okay. And that should be mostly unique. Then we need to not check the hash code because the hash code is not guaranteed to be the same in this case anymore. Okay? So we need to hurry this up. You can pick a large Mersenne prime. They are all ones in binary. Not all numbers that are all ones are primes. Like for instance 15. 15 is 4 ones, but it's not prime. It's got factors of 3 and 5. Okay. And this is going to overflow. Like the point of having a large number here is that I want it to overflow. Ideally. Yeah, all I care about is that whatever the prime of this is, or whatever value gets spit out of here, this has a very good chance of overflowing when multiplying it. And that's really all I'm trying to do. Because the overflow is just going to throw away the high bits and only keep the low bits, which are going to be mostly random. And then ORing together the results. So this is not guaranteed to be unique like my last implementation. And so because of that, we need to change this for equals to not just compare the hash codes. So instead what we want to do is compare this dot, and in this case we want to say var actual equals tic-tac-toe game of object. And then we can say, well, really, yeah, no, let's keep going this way. And now we want to say dot player 1 pieces equals actual dot player 1 pieces, and this dot player 2 pieces equals actual dot player 2 pieces. And that is a real check for quality. Okay. Let's see if the test pass. Oh wait, no, there was one more in player. There was one more. Not this player. And console player is now going to have an error because it looks at the board. Okay, so let's go put the board back. Only we're going to make it a function. And we're going to put it somewhere down here. And basically the way that this is going to work is we're just going to say enumerable. Okay, we're just going to say var result equals player ID array, new player ID array of 9 because it's tic-tac-toe. Return result. And then we're going to say for int I equals 0, I less than 9, I plus plus. Okay. Result of I equals player 1 pieces. Oh man, I'm gonna just implement a function here. Private bool, yeah, has flag, int value, int flag, return value and flag equals flag. Okay, and then we're going to say has flag of player 1 pieces and 1 I. Then we want to say player 1, player ID dot player 1. Okay, or has flag player 2 pieces, player 2, or player ID dot none. And I probably want to use that has flag everywhere else that I was just using flags. Like for instance here, has flags, I guess is a better way to say it. And this becomes has flags, all taken, all slots. And there was one more, I think. That could be implemented as it. Nope. Okay. This. Understand. Okay. Let's see if it builds. Not what I was looking for. Certainly wasn't. Tic-tac-toe does not contain a definition for board. Oh, right. Console player. It's get board. Oh, guess we were still killing this. Okay, let's see if it works. And secondly, let's see if it's actually faster, because that was the whole point of this. Okay. Okay, seems to be showing me some sort of values. You know, I got 4 warnings here. Oh wait, no, hold on. Yeah, okay, we're good. No warnings. Build succeeded. No warnings, no errors. So we go back to this. Oh, that's interesting. I'm in it right now, and it just built just fine, which is concerning. Weird. Okay. Culture of development, Monte Carlo tree search, source, MCTS, bin, debug, net core app. Oh, alright, we're just gonna try it. I mean, we're gonna try it. Guess we'll know in just a second if it starts spitting out insane stuff. I really sort of expected these numbers to not be so... I don't think it's actually updating this. I don't think it's actually updating this. These numbers should not be like uniquely increasing and all positive. I guess let's just try it. Whoa, the game is over. Fun. Player 1 is the winner. Let's go figure that one out. Okay, let's debug. This one crashes pretty easily, so let's just go figure out why it thinks whoever the winner is the winner. Oh wait, no, we said we wanted to run the test is terminal test. Unhandled exception. Expected winner of tie game should be player 1. Actual was none. Okay. F9. F5. F11. Expected. Tic-tac-toe. Apply move. Okay, next state. If the current player's move is player 1, which it is, then the player pieces is now 1. And cell number was 0. That is correct. Determine winner. Let's take a look at winning batches. We got a 7. Okay. Oh, I want cell group. This is the has flag that I need to fix. Has flags, pieces, cell group. Okay, we can stop this now. Okay, terminal. .NET build. Ooh. An object reference is required for the non-static field. Let's just make it static. There we go. Let's try that old .NET run again. Okay. Expected winner should be player 1. Actual was none. So let's get back to the debugging. So we want to go and cell 1 first. We're just going to do that. Current player's turn is none. Well, that's the problem. So it's somehow setting current player's turn to none. Okay, let's go and debug that. I need to get rid of this F11, F5, F11, F11. Determine winner. Has flags. Cell group 7. Pieces 1. F11. If the value and the flag equals the flag, which I have no idea what the return value is here. Come on. Get through it. Alright, we returned false. Hooray! And then we say the next player's turn, all taken, 1, all slots. If the player ID .winner is none, which is correct, and has flags, okay, that doesn't happen. The winner is none. Oh, it's not has flags, it's any. So not. Okay. One more time. And it passed. Okay, let's try running it one more time. We gotta actually change it to not be doing the test. Okay, .NET build. Okay. Alright, so we did increase the speed a little bit, and it appears to be still finding that the only thing that ties is the middle, which is good. Which is really good, actually. Spent almost all of its time exploring the middle. Also good. So, still not as fast as I was hoping it would be, but it's not the end of the world. I feel like there's some improvements that we could do. You know what? There is improvements. We could cram all of this into a single integer. And we could run it in release mode instead of debug mode. So we know debug mode is not fast. Let's just try that. C, release. And let's go take a look at the release build. Okay, cd cd space release ls cd space net core app 3.0 mc ts.exe. If we go to 0, okay, well, 36,000, so it did 1.5 times the work for being in release mode. I still think that, like, in a half a second, this ought to be up closer to 100,000. Like, I don't think it's impossible to get there. I want to say we can get there by just doing. We can just rename this to pieces. And then we just say pieces equals 0. Actually, this isn't really going to help that much, is it? Probably not. Yeah, I'm not even going to waste the time here. So, conceptually, we can cram it all into one 32-bit integer because we only need 9 bits to represent the pieces. So we can just put the first 9 and then shift it by 16 and have the second 9. In fact, we could probably put all of this into the same thing because these are effectively like 2 bits apiece. We got plenty of extra bits lying around. Let's go ahead let's go ahead and go through with the pieces thing, because I think that might actually help. We got pieces and OX, what, 16? No. 1FF. And then you got pieces right shift 16. So player 1 pieces are the first 9 bits, or the first 16 bits. And then you got pieces and pieces and pieces. Pieces and 0x1ff pieces right shift 16 plus 16 all taken equals pieces and 0x1ff or pieces right shift 16 same thing. And it's not next state, it's just pieces. I mean, definitely making this a lot harder to read, that's for sure. And then in this case, we can just say pieces.getHashCode. This dot pieces equals okay, that got easier. Where is the whole thing where you like get the board? Yeah, no, I did that right. Okay, I mean, let's see. Let's see. Let's go back to the program. Let's see if the terminal tests still pass. Come on. Okay. All right, that was interesting. Let's go and make it so that you can actually play it and see if it's... Again, the whole point of this was to make it faster. And loading memory locations is slower than just performing bitwise operations on an already loaded location. That's the the concept here as to why I think this will be faster. Even though the code is a whole lot uglier. Like, just atrociously uglier. Let's go kill this. Zero. 35,000. Okay, so we didn't actually make it faster. This is the first run. Let's try it again. That avoids the JIT. 35,000. Okay. Interesting. Alright, the correctness is still there. Now I'm like in a mode where I really want to make this faster. How can I make this faster? How can I make this faster? These are allocations. If we go, what all uses this? Expand successors. Yeah, no, that really needs to be an array. Okay. Can I avoid the allocations by giving it an array? It's this that's really causing the most pain anyway. Apply move is creating... What if I make it so that the state is recyclable? And then I just have a pool of states. I'm not going to worry about it. Okay. That's going to be it for today. I'm going to wrap this up because I got some stuff to do this afternoon. Thank you, everybody, for hanging out. I do really appreciate it. Today was actually kind of a lot of fun. I learned a lot about what's going on with this. I really thought it was going to be just a whole lot, like, better. I didn't really understand that you had to, like, actually put some work into it. I'm kind of interested to see what the improvements are after this now. Have a good rest of your day. Thanks. Yeah, thanks, man. You as well. I will be back tomorrow. I think I'm going to keep grinding away on this. I'm going to stop worrying about the speed of this. I think I'm going to implement a new game tomorrow, maybe Othello, or Reversi it's sometimes called, and then see if it's good enough to beat me. That's my plan. Having more than one... This is one algorithm we should not have to touch at all. Like, we literally should not have to touch this. We should just have to implement a new game, and it should be able to play it just fine. And that's what I want to try tomorrow. All right, so I will see you all then, and y'all have a good day.